So now that we're familiar with these ideas of exponentials, we can take a closer look at one of the applications that I mentioned in the last part, and that is compound interest. Okay, and here's the basic idea, right? When you have some principal P, right, some amount in dollars, and then you take this principal and you get some interest rate on it, okay, over some course of some number of years. Okay, so we can sort of begin to write this out. Our interest, right, is our principal times our yearly interest rate times t, the number of years. Okay, and what's important to note here, right, is the accumulated amount, right? So we'll call that A, right? So after 1 year, the amount that you have accumulated, you'll have your principal and then your interest, which you can factor that P out and get 1 plus RT. But what will often happen, right, is you will continuously accumulate this, right? You'll take this interest out after 1 year, then add it back into the account, and then all of a sudden you have a new principal that you're gaining interest on. Okay, and so this is often called the simple interest formula. But if we begin to compound, things get a bit more interesting, right? What happens after 1 year, right? Say call that A1. Well, in that case, t is equal to 1, right? And then we can just follow P times 1 plus R, which makes sense, right? But then what happens the second year, right? Now, our principal, right, the amount that we're starting with, is P times 1 plus R, and then we're adding on to that P times 1 plus R, which was our new P, times my rate, okay? And there's one additional factor here, and that's what happens to T, but in this case, we're calculating every year, right? So we're fine. T is just equal to 1. But if we begin to simplify this, we have 1 plus R plus R plus R squared, and this is actually a perfect square, right? This is P times 1 plus R squared. And if you keep calculating this, right, what you actually end up with, say you calculate A3, you're going to get P times 1 plus R squared plus P times 1 plus R squared times R. And if you carry through the math here, you get P times 1 plus R cubed. And you're able to show that this pattern actually continues. That when you compound like this every year, it's P, your initial principal, times 1 plus your interest rate, where that 1 plus the interest rate is raised to the power of the number of years. And this right here, this is an exponential. So the tools that we just developed can help us work with them, right? This all gives rise to something called the compound interest formula. And we've done the majority of the work for it already. It has one slightly more complex thing. Rather than R and T, there's a division by M and an extra factor of M here. And that's based on the fact that we assumed here that you're compounding annually, right? If you compound more often, right, take that interest and add it to your principal more often, well then the rate that it's growing by, right, where R is our yearly rate, the rate that it's growing by is slower, but the exponent is higher. Okay, and we'll look at some of the intricacies of that in just a second. Um, but let's define all of these variables. A is my accumulated amount at the end of t years. P is my principal. R is the interest rate per year. So, maybe something like 8%, right? M, your book calls this the number of conversion periods per year. But in plain English, this is the number of times compounded per year. And then T is our actual variable here, and it's the term / number of years, right? These three values here, right, these are given instances in the problem, right? Versus T and A, T is our variable, and then A is the output, okay? So we can run a quick example to see sort of what this behavior is actually like. So let's say find the accumulated amount after 3 years. We say invest $1,000 at 8%, and then we'll compound annually, semi-annually, quarterly, monthly, and daily. Okay. And we'll actually sum this up in a table, I think is the easiest way to see it. And so we'll need these different periods here. Annually, let's say semi-annually, quarterly, monthly, and daily. We'll need the period that goes along with it, right? So, right, obviously annually is going to be 1, semi-annually is 2, 4 quarters, 12 months, 365 days, okay? And let's begin to fill this out, right? And annually, we have A is my principal, which is $1,000, times 1 plus 08 to the 3, right? We're just cubing it because our M is 1. And if you put this into a calculator, you're going to get 1,259.71 or so, okay? One of the things that sort of comes out of some of this work is things start to get a little bit less friendly if you don't have a calculator. For the sake of exams and quizzes and homeworks, I am absolutely fine with and actually prefer just leave it in this form. For the sake of this lecture, I'll be converting some of them so we can actually take a look at the behavior, though. Okay. So semi-annually, we still have the same principle. 1 plus, my interest rate is still 0.08, but now we're doing it twice a year, so I need to divide it by 2, but I'm compounding twice as often, okay? And when you run that through, my output goes up a little bit, $1,265.32. Again, once again, this is approximately, okay? For quarterly, once again, $1,000, 1 plus 0.08, sorry, this time over 4, the 4 times 3, and that guy comes out to $1,268.24. And then for monthly and daily, I assume that from these, you can calculate those on your own to verify. We have 1,270.24, and daily is 1,271.22. Okay. So we can see that as you compound more often, right? The amount that you have after 3 years goes up. Maybe not substantially, but there's a difference of right around $10, $12 there, and $10, $12, that's lunch if you're smart about it, right? But it sort of begs the question, right, of our interest rate here of 8% gave us a different number depending on how often we were compounding. And so, at that point, it's not necessarily the most useful thing, right? It's 8% per year, but compounded monthly, it just, it doesn't quite doesn't quite make the most sense, right? It would be nice if we could have a simpler value to where we could just do something like this, right? Because this is comparatively much easier to calculate than something like this, or even what you would have to do in the case of the daily. Okay, something like what's called an effective interest rate, right? And the effective interest rate is, the rate you would need for this to be the case. Okay, and here's how you calculate it. Right, we can find a formula taking t to be 1, right? We're looking for something like this, 1 plus, we'll say r sub EFF, right, my effective rate. We're looking for some rate that, where these two expressions are equal, right? Because this is what 1 year compounded monthly, or whatever our value of m is. And if we set these two equal, well, that's going to give us an equation pretty quickly. 1 plus r over m to the m. right? First I can divide by p because p is a positive number, and then I can subtract 1. And I get that my effective interest rate is 1 plus r over m to the m minus 1, right? Where r sub EFF is my effective, interest rate. R is what's called the nominal interest rate, the same interest rate we were working with in the last case. And then M is the number of periods per year, right? The number of times that we compound. And so, we can look at what is the effective interest rate of, say, R equals 0.08 or 8%. Compounded, and we can take a look at them one at a time. If we just go annually, well, this one's not too interesting, right? 1 plus 0.08 minus 1 is 0.08, right? It's a nominally, annual interest rate, so the effective annually is just the original guy. But here, if we're going semi-annually, now things are a bit more interesting. My effective interest rate is 1 plus my interest rate over 2 squared minus 1. And once again, you're going to need a calculator for this guy. It's going to be 0.0816, so 0.1%, almost 0.2%. If we go monthly, sorry, I guess we should go quarterly first. My effective rate is 1 plus 0.08 over 4, because we're doing quarters, to the 4 minus 1. And then it comes out to about 0.0824. Okay, so 0.25% more. And then, once again, for monthly, you guys can verify this on your own. My effective is about 0.083, and then daily, it's about 0.0833. So you get, 0.33% extra by compounding daily over compounding annually, which is, pretty nice, but it starts to ask a similar question. As we compound more and more often, our value goes up, and it seems to slow a little bit, though, right? The jump from annually to semi-annually is, right about $5, and the jump from monthly to daily is $1, right? Going from 1 to 2 versus going 12 to 300. It sort of asks the question of what happens as you compound more and more and more often, rather than daily. What if you did it every 12 hours, every hour, every minute, every second? What if you compounded continuously? But all of a sudden, this is a limit question, right? If we're going to continuously compound, well, then we're looking at the limit as m goes to infinity of p times 1 plus r over m to the m times t. Okay. But there's a few things that we can sort of factor out here, right? My t is not dependent on any of this, so it can come out. Same with my p. So this is p times the limit as m goes to infinity of 1 plus r over m to the m, and that whole limit is to the power of t. And this is where we need to make a bit of a clever substitution, okay? Let's say, for example, u is m over r, okay? We still have our p. We're going to limit as m goes to infinity of 1 plus, well, if u is m over r and we have r over m, that's going to be 1 over u. And then further, if u is r over m, then m is u times r. And all of this is to the t. But notice that as m goes to infinity, all of a sudden the statement doesn't have any m's in it. But r is a fixed value, and so as m goes to infinity, u is going to go to infinity. Further, this r, for the same reason that the t hopped out, this r can hop out, and our function looks like this. The limit is now u goes to infinity of 1 plus 1 over u to the u to the rt. And maybe this looks a little bit familiar to you because this is our definition of e. So when we continuously compound our interest, right, every possible instant we're taking whatever interest we accumulated and adding it into our principal, we get the part formula, right? My principal times e to my rate times my time. And if we sort of go to that previous example that we've sort of been working through for a bit, say my principal is 1,000, my rate is 0.08, and we're going for 3 years, right? This part formula is significantly simpler to set up, right? Calculating this, you're going to need a calculator. Like I said, for the sake of quizzes and exams, this is the form that I want. But if you do want to evaluate it, you will need a calculator. It's going to come out to $1,271 and about 25 cents. So what that tells us is that if we compound every possible instant, you're going to make about 3 more cents over the course of 3 years.